is just purely random. There is a non-zero probability that is true. Unlikely, but. All right, so what we have so far in trying to explain this electric phenomenon, if we're dealing with vectors and I have two charges, we have force. So the force on 1 from 2 would be this electrostatic constant, or 1 over 4 pi epsilon sub naught, Q1, Q2 over R squared, R2 hat. So that would be the force between them. So if we're talking about vectors and you have two charges, then force is a way of dealing with it. If I have one charge, I can't have a force with just one charge, so I can deal with electric field. So my electric field, K cubed over R squared, R hat. From a unit point of view, the SI unit of force is the Newton. And the SI unit for electric field is Newton per Coulomb, SI. And that's basically chapter 20, 23, 24. But if we're dealing with scalars, if I have two charges, I can talk about it in terms of potential energy. The formula being case of E, Q1, Q2 over R. Now, do be vigilant here that at some point when I'm writing a potential energy formula, I know for gravitation and for this, I know it's supposed to be R on the bottom, but out of habit, I sometimes write R squared, so just watch out for that. No direction because it's scalar, and the SI unit is the joule. And obviously we have a blank here we need to deal with. I guess technically plus a constant, although often that constant is 0. Now, when we went from force to electric field, we took out one of the charges. Because again, we're only dealing with one charge here, so we have to somehow, it's the idea that there's something that exists there before the second charge shows up. And so we do the same thing here. So we have our KE Q over R plus a constant. This is known as the electric potential. The unit of an electric potential. Well, basically, I took my potential energy formula and just divided by a charge, so the unit should be joule per Coulomb, which for some reason they found too much to write down, so they came up with an abbreviation, the volt. I do want to point out, I'm not talking about voltage. Voltage is related to this, but this is not voltage. And really, to make matters confusing, so the SI unit for electric potential is the capital V for volt, and the symbol for electric potential is the capital V. So we are now faced with, in math class, V would equal 0. In physics, the electric potential equals 5 volts. So from context, you need to realize these two V's do not mean the same thing. So this is electric potential, and this is volt. Usually the big clue is that the unit comes right after a number. So, let's say I have a charge here of, let's see, nanocoulombs will probably put it right.
Are we allowed to put joules over coulombs?
Yep.
Well,
Yep.
Just so it clears up the crap.
Should be a capital C. It's getting worse and worse as I do it, but it's joule per coulomb, that's perfectly fine.
Okay.
I'll probably stick with volts, just out of habit.
Okay.
All right, so if I've got a positive charge here, and let's make it, I have a 4 nanocoulomb charge. If I am 1 meter away, what is my electric potential? And again, let's assume, for this problem, assume V is equal to 0 at R equal to infinity. So like a jug, KQ over R. And K being 9 times 10 to the 9th is sufficient.
Volts.
Yep, 36 volts. If I go another meter out, what's my electric potential?
18 volts.
If I go another meter out,
12.
I think I heard you say that.
Yeah.
And we'll do one more. Go another meter out.
9 volts.
So my electric potential drops the farther out I go. Even if I tacked on the constant, it would still get smaller the farther out I go. If I put a positive charge here, that positive charge we know is going to go to the right because it's going to lose potential, gain kinetic, or it goes in the direction of the electric field created by the source, or like charges repel. If I put a negative charge here, we know it's going to be attracted. And so we have a generalization here that positive charges want to move to lower the electric potential. Negative charges want to move to higher the electric potential. Let's see if it holds true for negative charges also. So if I have a negative 4 nanocoulomb charge here, then if I'm a meter away, this is negative 36 volts, given the same restriction as before. Another meter goes by, I'm at negative 18 volts, negative 9 volts, negative 12 volts. Negative 9 volts. If that rule holds true, then if I put a positive charge here, it wants to move to a higher, positive wants to move to a lower electric potential, which would be in this direction. Negative charges want to move to higher electric potential, which puts it going in that direction. Going with the classic math thing that negative 9 is bigger than negative 12. Again, because these are scalars, the negative sign is not indicating any direction whatsoever. So that's the second part of the explanation about why the charges will retract or repel. The first part is electric potential. Increases when going toward a positive charge and decreases when going toward a negative charge. And the opposite applied. If it increases going towards a positive charge, it should decrease going away from a positive charge. We're going to take a break soon here. I want to explain what voltage is, and then we'll take a break. Questions here? So I'm just going to take this bit that we have right here, and that is irrelevant to what I'm doing next. And actually, I don't really care about that. What I care about is I have these potentials right here. So I start at the negative, I start at the 36 volts and I go to the 18 volts. What is my change in electric potential?
18 volts.
No.
Negative 18 volts.
Yes, it's always final minus initial. So I go from here to here, it's negative 18. If I go from 36 to 12, so that would be for this one. What's my change in the electric potential from 36 to 12?
Negative 24.
So if instead I decide to go the really bizarre route, I start here, I go through the 18, I then go through the 12, I hit the 9, I go all the way around here, pass through the 36 again, and then end up at the 18. What is my change in electric potential?
Negative 18.
Yes, it only matters where I end and where I begin. Similar to some scalars in that respect. But ultimately we're looking for what is the change in electric potential. This is voltage. So voltage can also be defined not only as the change in electric potential, but sometimes called the electric potential difference. And I have before in the past given a problem, and I said, what's the voltage? And then I said, what's the electric potential difference? And then I get disappointed when people, not everybody recognizes that I'm asking the exact same question. Now, some textbooks play really hard and fast with this, and they put it into delta V when they're talking about voltage, and they put it into capital V when they're talking about electric potential. Some textbooks do fast and loose, and they just use capital V no matter what without sticking the delta in front of it. Here's the thinking for the books that do that. I know that my voltage is my final potential minus my initial potential. Since electric potential is KQ over R plus some constant, this gives me the freedom to decide where 0 is wherever I want. Therefore, I can choose, if it's not already chosen for me, I can choose my initial potential to be 0 volts. Therefore, my voltage is just equal to my final potential, and since I'm only dealing with one potential at this point, I can just call that potential, or voltage, Or just use capital V for the same thing. Frankly, I can't remember. I think your book plays hard and fast, and they stick hard and slow. They stick to delta V when they're talking about voltage and V when they're talking about electric potential. In class, I will stick to the convention of trying to keep them separate. Although I won't be shocked if I go the lazy route every once in a while. Similar type reasoning for textbooks that use displacement and position as identical. Since you can establish zero wherever you want, why not just establish your starting point as zero, and then your displacement and your position are the same. All right. I think on that note, let's take a break. If you have questions, you can ask them when you get back. And yeah, stretch your legs, take a nap, whatever. All right. So I got a ring of charge. Total charge 5 nanocoulombs, and the radius of this is 0.3 meters. At the very center here, what is the electric field? And what is the electric potential? Assuming B equals 0 at R is equal to infinity. And I sort of developed this thing over the past couple of years of giving you a shape and then asking you to find the electric field and the electric potential at a particular spot. So just sort of gear yourself towards getting some question of some shape. All right, so the electric field at the very center.
Zero.
It is, why?
Since it's a ring of charge and it's, the electric field is equal from every direction. So it cancels out in the middle.
Yeah. So if I have a charge here creating an electric field in that direction, there's something on the other side of the circle that's creating an electric field in the other direction, they cancel out. So the electric field is 0 at the center. The electric potential, however, is not. Now, you might see how to find the answer already. I'm going to do it the longer way, and then sort of, hopefully it will show why there's a simpler way of solving this particular one. But if I have a distribution of charge, I start out with creating a differential. I find out what is the electric potential from something right there. So I have some dq. So my partial, or my differential of my electric potential is equal to K dq over R. And that subscript is supposed to be an E, but C also works for Coulomb, so electrostatic if it's an E, whichever letter you like. And so integrate both sides. I'll keep it on the inside for right now. All right, so dq. I need to somehow get them in terms of, well, no, you know what, we'll do it a slightly simpler way than what I was about to do. R here is the distance from some point on the circle to the center. It's a circle. The math people tell me that circles have a constant radius. And so therefore this R here is a constant, and so we get the integral, we get Ke over R times the integral of dq, which is just Ke R cubed. And so in this particular case, even though I started out with doing an integral right there, That center is the exact same distance away from all of them. We aren't dealing with vectors here, so there's no cancellation going on. And it's kind of like we're treating I got a point particle of charge 5 nanocoulombs, and I'm a distance 0.3 meters away. So 9e9 times 5e negative 9 divided by 0.3. So that's 150, 15, so 45 divided by 3 is 15 times 10, yeah, I think it's 150 volts. Now let's do one that actually requires calculus. I have a finite line of charge. Let's make that 0.4 meters. I have some point 0.2 meters from the middle of this line of charge. And the question is, what's the electric field and the electric potential? Same assumption as before. Why don't I just write it up at the top of the board just so that it will cover the board. Assume V is equal to 0 at R is. Now we've done something very similar for this with the electric field, except we had an infinite line of charge. This is a finite line. We do have symmetry still involved here. I conveniently made this closest point of that to the line to be the middle here, so that I don't have to worry about getting vertical components. I saved that for your master set. So my final electric field will be to the right. Let's give it a charge of 5 nanocoulombs